Welcome to TopperHQ, our own study hub. All right, let's dive into one of the most beautiful, most profound ideas in all of science. We're going on a hunt for a single, simple rule that might just run the entire universe. I mean, what if I told you that all the complicated laws of physics could be boiled down to just one core idea? It sounds like something out of a sci-fi movie, but it might be way closer to the truth than you think.
Yeah, that's a pretty bold claim, right? It's such a huge statement that it feels, well, a little bit spooky. The idea that everything, from a planet sweeping around the sun to the bizarre behavior of quantum particles, is all following the exact same single instruction. So what is this rule, and where in the world did it come from? Well, you might be surprised to hear that the story starts with a very practical 17th century challenge.
So let's hop in our time machine and zip back to the 1600s. A challenge was posed to the smartest people alive, and the question was actually pretty simple to ask. Imagine you have a point A up high and a point B down low. If you want to build a ramp for a ball to slide from A to B as fast as humanly possible, what shape should that ramp be? This puzzle, the problem of fastest descent, absolutely stumped some of the greatest minds of the era.
Now, what do you think? Your gut instinct, my gut instinct, pretty much everyone's gut instinct screams that a straight line has to be the fastest, right? It's the shortest path, after all. But nope, that's the wrong answer. Think about it. If you make the ramp super steep right at the beginning, the ball picks up a ton of speed right away. So even though the curved path is technically longer, that initial burst of speed means its average speed is way higher. The curved ramp wins the race every single time. The real question is, what is the perfect curve?
Even the great Galileo took a crack at this. His best guess was that the fastest path was the arc of a circle. A really good guess, but not quite correct. So, decades later, in 1696, this brilliant and, let's be honest, kind of showy mathematician named Johann Bernoulli throws the problem out there as a public challenge, basically to prove who is the smartest of them all. And at first, nothing. So they extended the deadline, and a copy of the problem eventually found its way to Sir Isaac Newton.
Now, you have to imagine, Newton, at this point in his life, was kind of done with physics. He was running the Royal Mint and was apparently pretty annoyed at being bothered. But the problem was just too juicy to ignore. The story goes that he came home from work, saw the problem for the first time, stayed up all night, and had it completely solved by 4 a.m. And get this, he submitted the answer anonymously. But when Bernoulli saw it, he wasn't fooled for a second. He famously declared, "I recognize the lion by his claw." The solution was just so elegant, so powerful, he knew only Newton could have done it.
But here is where the story gets a fantastic twist. Newton's solution was, of course, brilliant, but Bernoulli's own solution was arguably even more creative, more profound. And that's because he found the answer by looking at a totally different area of physics, how light behaves. He made this incredible conceptual leap that would literally change everything. This was the key that unlocked the whole thing. Years before, a mathematician named Pierre de Fermat had noticed something really strange about light. You know how if you stick a straw in a glass of water, it looks bent? That's because light bends when it goes from air to water. Fermat realized light doesn't take the shortest path, it takes the fastest path. It's almost as if the light ray knows the quickest route to take, even if it's not a straight line. This was the first clue that nature seems to be optimizing.
And this is where you can really see Bernoulli's genius. He had this amazing what-if moment. He thought, what if the sliding ball isn't a ball? What if it's a ray of light? He imagined gravity as a series of invisible layers, like different densities of glass, that the light would travel through. As the object falls, it's like light entering a medium where it can go faster and faster, causing it to bend. He then just applied the math he already knew for light refraction, Snell's law, to this imaginary setup, and it worked.
And the answer that popped out? Not a circle. The perfect fastest path is a shape called a cycloid. If you've never heard of it, it's a really cool curve. Imagine you put a dab of paint on the rim of a bike tire. As you roll the bike forward, the path that dot of paint makes through the air, that's a cycloid. An astonishing solution. Bernoulli had solved a mechanics problem using optics, revealing a deep hidden connection in the universe. But this was really just the beginning of the story.
Okay, so this incredible discovery got one of Bernoulli's own students thinking. His name was Pierre de Maupertuis, and he started wondering, why time? Why would nature care specifically about minimizing travel time? Maybe, he thought, time is just one piece of a bigger puzzle. Maybe there's a more fundamental quantity that the universe is always trying to minimize. And he gave this mysterious quantity a name, action.
His first attempt to define this action was pretty intuitive. He just said it's the mass of an object times its velocity times the distance it travels. Simple enough. The bigger, faster, or farther something moves, the more action it has. And his grand claim was that for any possible path an object could take, nature will always choose the one that minimizes this total action.
For Maupertuis, this was way more than just math. It was a deep philosophical truth. I love how he put it. He called action the true expense of nature, which the universe, like a cosmic accountant, is always trying to make as small as possible. It's a really beautiful and powerful idea. Unfortunately, the scientific community at the time, they hated it.
He was absolutely torn apart. His own friend, the famous writer Voltaire, mocked him publicly. He was accused of plagiarism, of doing bad science. The biggest problem was that his idea was mostly intuition. It didn't have the solid mathematical foundation it needed to be taken seriously. His entire legacy was on the verge of ruin, but it was saved by one person, the mathematical giant Leonhard Euler.
Euler saw the nugget of pure genius in Maupertuis's idea and started building the rigorous math to support it. But the person who truly perfected it was an incredible, self-taught, 19-year-old prodigy named Joseph Louis Lagrange. Together, Euler and Lagrange took a vague philosophical hunch and forged it into a cornerstone of modern physics.
So what exactly did they create? Well, they built a whole new way of looking at the universe. See, Newton's physics is all about forces, pushes and pulls. But this new method, it kind of ignores forces altogether. Instead, it focuses on something more fundamental, energy. And that new perspective is what makes this whole principle so incredibly powerful. Over the next century, the definition of action got a major upgrade. It evolved from Maupertuis's simple formula into something more abstract, but far more powerful. The modern definition is all about two types of energy: kinetic energy, which is the energy of motion, and potential energy, which is stored up energy. The action is found by taking the kinetic energy, subtracting the potential energy, and then adding up that value over the entire journey. It's a weird calculation, but it turns out to be exactly what nature is trying to optimize.
So this special quantity, kinetic energy minus potential energy, is the absolute heart of the whole thing. It's so important that it gets its own name, the Lagrangian, which we just call L. So the principle of least action says that the real path an object follows is the one that makes the total action, the sum of this Lagrangian over time, as small as possible. It's truly the path of least resistance in a deep mathematical sense.
So at this point, you're probably thinking, okay, that's a lot of math. Why not just stick with good old F equals ma? And that is a fantastic question. The answer is that for some really complex problems, using F equals ma is a complete nightmare. The Lagrangian approach, though, gives us what physicists call a machine. You just feed the energies into it, turn the mathematical crank, and out pops the right answer every single time. Let me give you a perfect example. The double pendulum. This thing is famously chaotic. If you try to figure out its motion using Newton's laws, well, good luck. The forces are constantly changing direction, the coordinate systems are moving, it's just a total mess of vectors. But if you use the Lagrangian, it's almost laughably easy. You don't care about forces or directions. You just write down one simple expression for the kinetic energy of the system and one for the potential energy. You plug those into the machine, the Euler-Lagrange equation, and it just spits out the correct equations of motion. It turns a nearly impossible problem into a straightforward exercise. Now, I have to make one quick but important correction here. All this time we've been calling it the principle of least action, and that's the common name. But physicists call it the principle of stationary action. Here's an easy way to think about it. Imagine you're on a hilly landscape. The path nature chooses isn't always at the bottom of a valley. It could be right at the peak of a hill. The key is that at that exact point, the ground is flat. A tiny step in any direction doesn't change your elevation. That's a stationary point, and that's what nature is really looking for.
And this all brings us to the final mind-bending question. From a simple thrown ball to Einstein's general relativity to the spooky world of quantum mechanics, this principle just works. It holds up everywhere. But why? Is it just some elegant mathematical coincidence that happens to give us the right answer? Or is the universe, in some profound sense, actually calculating all possible paths and choosing the one with stationary action? Is this principle a clue to the fundamental operating system of reality itself? That's definitely something to think about.